Question number 4 for the homework comes from the 2013 E&M portion of the exam. We want to know which position the switch should be moved to charge the capacitor. And that is actually going to be position B, because if we move it to A, there's no battery hooked up to the system that can effectively move charge around the circuit to charge the capacitor. So we need to move it to B in order to charge it up. Now it says, on the diagram, draw a voltmeter that is properly connected to a circuit in a manner that will allow the voltage to be measured across the capacitor. One small thing I want to say here. An ammeter looks like this. You'll also see it drawn like this. Okay. A voltmeter looks like this. You'll see it drawn like that. And you know what? Actually, I'm just going to get rid of it. I'll just draw A for ammeter and V for voltmeter, and I'm going to explain what these things do. So this is the symbol for an ammeter. That is just terrible writing. So this is an ammeter. It measures current. This is a voltmeter, and it measures voltage. Just to put this out there, if you want to measure current in a circuit, you always put the ammeter in series with the thing you want to measure the current of. And with voltmeters, you always put them in parallel. That's just the rules. Okay? How those things work, we're going to get to a little bit later. But for now, if we want to measure the voltage across this capacitor, we're going to hook up our voltmeter right there in parallel with it. And that's just a measuring device, and it will have no effect on the circuit. So that is part A, number 2. Now for part B, it says after a long time, you move the switch to discharge the capacitor. So now we've moved the switch back to A. Couple of things here. We want to determine tau, and we've got the voltage across the capacitor as the capacitor discharges. So after these various times that pass. And our goal is to determine tau by plotting a linear graph. So first of all, there's a lot going on here. Since this is an RC circuit, and we've put the switch on to A, now we've done separation of variables in class. I want to just say a couple of things here for this particular situation. So when we have the switch at B, at first we have a current E over R going through the resistor, and then an infinite amount of time passes, and there's no current going through the resistor, and all of the voltage is on the capacitor. So what I'm going to do here is, in a different color, I'm just going to write letter B, and I'm just going to say setting up for part B. So first, as time goes to infinity, okay, I across the resistor equals 0. And we know that the voltage across the battery minus the voltage across the capacitor minus the voltage across the resistor equals 0. So as time goes to infinity, the battery EMF does not change. We have the voltage across the capacitor, which I'll leave as VC, and we know that the voltage across the resistor, being I times R, is going to be 0 times R, which is 0. So as time goes to infinity, the voltage across the capacitor is simply equal to the voltage across the battery. Now, as we continue with this, let's also get the charge across the capacitor at time equals infinity. That's going to be CV, which is going to be the EMF times the voltage across the capacitor. Let me say that one more time. The charge across the capacitor is going to be C times the EMF across the capacitor. There we go. Now, after we put the switch back to A, we know that negative voltage across the capacitor minus the voltage across the resistor equals 0. So I'm just going to put these two little things in a square, in a little box, because we're going to use them later. So we can say negative Q over C minus the current across the resistor dQ dt, minus the resistance dQ dt, that's R times I, that's IR, for just Ohm's law for resistor, equals 0. Now we can solve this using separation of variables. These, by the way, are the initial conditions that I put in a box. So I'll call those ICs for initial conditions. Now, we did this work in class using separation of variables, but I'm going to actually repeat it. So the answer we're going to get, I'm just going to write it up here, is what we're going to get is that Q across the capacitor is going to equal Q naught e to the negative t over RC, which for this circuit is going to be Q equals C V of the battery e to the negative t over RC. Okay, so that's the charge across the capacitor. One other thing I want to note is if we divide both sides by C, we get an equation EMF e to the negative t over RC, where EMF is the voltage. This E stands for EMF, voltage of the battery. Q over C is the formula for the voltage across the capacitor. So what this tells us as a function of time is we get a bonus formula. One formula that we get is the charge as a function of time. Another formula that we get is that the voltage across the capacitor as a function of time is going to be the EMF e to the negative t over RC. All right. Continuing with that. So that's what we're going to solve for. This is something I think we might have memorized by now, but I just want to do the separation of variables really quickly. I'm going to do a quick version of it. So what we're going to get is that Q over dQ over Q is going to equal negative dt over RC. We'll integrate both sides. We're going to get that ln of Q equals negative t over RC plus the integration constant C. When we solve for C, we're going to get that C equals the natural log of C times the integration constant C, which I'll just give these little things to so that these little wings to it so that we can distinguish it from the capacitance, is natural log of C times the voltage. And so when we rearrange, what we're going to get is that Q of t equals C times the voltage e to the negative t over RC. All right, so the facts that we need, this fact and that fact. So I've kind of set up everything that I need to do part B. Now, we want to determine the time constant tau of the circuit from the slope of a linear graph, and we have voltage here. So let me just bring down that the voltage across the capacitor is going to be EMF of the battery e to the negative t over RC. And our goal is we want an equation of the form y equals mx plus b. So here we go. This is a little bit trickier than things we've done before. So let's just remember one other thing. The time constant tau is equal to R times C. So here we go. Natural log of the voltage across the capacitor, which I'm going to actually put that little subscript there so that I know that I've labeled things according to my differential equation. Natural log of V of C equals, and you know what, actually I'm just gonna, just to be careful, let's just bring this down here so that we know what it is that we're doing. Right there. Now we're going to linearize this equation. This is a new way of doing it because I know that when I give you an equation like y equals ax, f equals ax squared, you plot f versus x squared and the slope is a. We've done things like that. Here, when we have exponentials, it's a little bit of a process. So watch this and memorize how to do it. This is a new algebra trick. How did I know how to do this? Experience. Now you're watching it, and you're going to have to learn how to do this too. So this is going to be the natural log of VC equals, I'm going to use a log rule here, natural log of E plus negative T divided by RC. All right. Let me multiply everything through by -1. So I'm going to get negative VC. This is not the only way to linearize it. I'm just showing you one way. Equals T over RC minus the natural log of the voltage of the battery. So just to put this out there, this is going to be our y variable. 1 over RC. So M is going to be 1 over RC. T is going to be our x variable, and B is going to be negative natural log of the EMF. I can talk you through this slowly if you come to see me. Write it out like 6 or 7 times is really the way to sort of get this down as to what fits where. I'm basically taking these terms, plotting them as a line, and I'm making it look like a line equation so that I get a slope. Okay? It's just an experimental technique used in physics. Linearizing equations is a really useful thing in experimental physics and in engineering, and we do it here. So, what that means is that if I were to plot some things, my plot would be minus the natural log of V, okay, versus T, okay, and I'll get a line that looks like this with a negative slope, and this slope will be -1 over RC. Okay, that's the idea. Okay, now with that in mind, let's go ahead and get these natural logs. So that's going to be -5.53, -4.30, -3.50, -2.30, and -1.79. All right. Now we're going to go ahead and we're going to set up our axes and plot. So I have here, I'll make this 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, and 60 seconds. And I'm going to actually count backwards here. So this will be -6, -5, -4, -3, -2, -1, and 0. So this will be the natural log of V versus time, and our slope is going to be 1 over RC. So just kind of going here at 246, albeit about 5.53. At 18 seconds, albeit about 4.3, maybe a little bit lower. At 30 seconds, I'll be at about negative 3.5. And 42 will be at negative 2.3. And 54 is going to be at about negative 1.79. So right about there. And we're going to try to draw a line through this. Something perhaps like this. And I just want to be careful about where I'm drawing my line. And I'm going to try to be careful. I'm going to try to trace over this. I may not be successful. Probably not going to be, but that's the secret of a drawing tool. All right. Now, I actually worked this out before, and I picked 2 points off my graph. I had one here, which was 56 and 1.4. Just going for absolute values here. And I had another one that was like, it was 36 and negative 3. And when I got my slope here, my m, so it says from the line proceed to determine m was negative 1.4 minus negative 3 all over 56 minus 36, which was negative 0.08. I need the negative of this slope. Negative 1 over m is my time constant tau, which was 12.5 seconds. I see a lot of people getting the slopes and just assuming that's the answer. Careful with that. All right, now let's get the resistance from the time constant. So for part I, we have tau equals RC. 12.5 equals R times 1.5 microfarads. By the way, just so you know, when you divide by micro, that gives you mega. So we're going to end up getting 12.5 divided by 1.5. And that's going to give us 8.3 mega ohms. All right. Now, on the axes, use a dashed line if the capacitance was greater. Okay, so for part 2, okay, bigger C means a bigger tau. And to get a bigger tau, that means we need a smaller slope because we need a smaller number to get a bigger reciprocal. So for part 2, the line could look like this. All right, so that is the 2013 AP question.